Hi everyone. So today we'll be discussing optimizing recipe formulation using machine learning, sequential learning, and design of experiment. I'm Junaid Mahmood, and I'm working at Danone RNI in Utrecht as process technologist. So before we actually go to discuss the topic, I would like to discuss a little bit about Danone. So our mission is actually bring health through food to as many people as possible, and through our diverse portfolio, which focus on being healthy, we source from local markets, being sustainable, and being innovative. Now, you may be familiar with most of our global brands, Activia, Aptamil, Avian, or Alpro, but we have huge market also consisting of local brands. Now, if you know this, then most of our products they are consist of either food or food derivatives, and of course there is water. That means we deal with a lot of recipes, and when we are working with recipe formulation and thinking about innovation at Danone, what we want to do is we want to maintain highest standard, which results in very amazing taste, but we want to also maintain very good nutritional value, and we want to continuously innovate based on our consumer needs and what they like. Now, it's not an easy thing because there are numerous challenges when you want to innovate food-based products. First of all, consumer preferences may change from one year to the next one, and being more focused on sustainability right now, that means we need to keep on innovating. Secondly, we need to comply with the food safety regulations, which may result in one product which is being okay in one market, but it may not be okay in the other one. And also, we want to be our products to be inherently safe because most of our products goes for babies and sometimes even for patients who cannot take food orally. Then we want to actually balance the cost of our product. We want to maintain the highest quality that we can, because you can get really good quality, but if it's costly, no one is going to buy that. And given this in mind, usually when we are innovating, our product workflow cycle looks like this. This is actually quite generic, and any food company who is making food-based products will be following similar workflow. So at the start, it starts with either a new product ideation, or we have done our market research and we want to change certain properties of our product. Then based on that, we go to our ingredient selection and process selection. Now, ingredient and process selection goes hand in hand. One process that may work for certain type of ingredient may not work for the other one. So this is kind of a cyclic process where we are deciding our ingredients and process based on what kind of nutritional value they bring, are they sustainable, and when it comes to process, then if they are scalable, efficient, and if we can actually, the process we are using, it doesn't add to the cost of the product itself. Then the next step is actually prototype development, which we mainly do at our labs in R&I centers. And this is where we run our small scale lab trials. We do our flavor profiling and we optimize certain processes, or we go back to first step again and we choose a different ingredient. Once that is done, we go to our pilot plants where we look for scalability of the product. Then finally, we are doing a factory trials. And once all of this is done, the last step before we can put that into market, we need to do shelf life and stability testing. And certain type of product require regulatory approval, but not all of them. So it depends on the type of products that there is. Now, for lab scale, for pilot, and for factory, the way we are characterizing our product is based on how it tastes, like organoleptic properties, and it's certain other properties, it's processability, like viscosity and this kind of thing. So these become the product characteristics based on which we are optimizing our process. Now, in today's project that I'll be discussing, that we are mainly focusing on lab scale lab scale trials, and for which we have three main components: ingredient, process, and then experiments itself. So when we just only focus on ingredients and process, what we are actually focusing on is macro and micronutrients. Of course, they need to be part of the product, but then product needs to taste good. And of course, I've just discussed the shelf life part. Then there will be preservatives and stabilizer, and then there are texturizers, which helps product to be overall our when it's going through the process plant, it makes it more processable. And when we think about the process selection, then we could have temperature control, mixing, blend, processing speeds, and all other kind of different processes. And these are the decisions which are made beforehand, before we are going to the lab trials, or we are doing our lab trials, we are coming back to these ingredients and selections, and we are changing them, whatever makes more sense in terms of typical product. Now, when we think about ingredients, when we're testing these ingredients, we are testing them based on their functionality, whether they are like whatever their need is in terms of micronutrients, like if we want to put certain minerals or vitamins in, then their sensory characteristics, how they're gonna taste, and then what are the regulatory needs. And based on that, we can define minimum and maximum level of each ingredient. And then when we are doing these trials at lab scales, we are actually testing how each ingredient is affecting the product characteristics. And those are written over here: taste, texture, and stability. However, when it comes to maximum limits of certain ingredients that we can put in any formulation, that is usually constrained by its regulatory needs, and especially for flavors, sugars, and preservatives. And then we need to be aligned well. We need to remain below well these certain limits. So for this particular project that for which we used machine learning and sequential learning and DOE together, for which we wanted to optimize taste and texture. And for this, we were actually looking at 11 different ingredients, and we wanted to find a combination of either single, double, or triplet, which enhances this taste and texture. And then we have 7 different goals. For 3 of them, response variables, which we wanted to minimize, 2 of them we wanted to maximize, and 2 rest of them we wanted to keep them constant, so that even if we put these combination of ingredients, it doesn't change these 2 particular molecules. Then there were certain regulatory needs, and that is that if it's a single out of these 11, if we are putting single ingredient, then we can go to maximum of 1, and 1 over here is a level in our terminology. And if we think about DOE, then that means this is a maximum amount of the ingredient that we can use. Now, if we combine 2 of them, then we can use maximum only 0.5. And similarly, if we combine 3 of them, then maximum is 0.33. So these are the constraints in which we needed to find out which 3 ingredients results in better taste or texture. So now if you think about overall combinations, there are total possible combinations of 2 ingredients, 55. Then if there are 3 ingredients, then 165 possible combinations are possible out of these 11. And if we combine all of them, that is 231 total combination. And then doing experiments for each of these combinations is already just too much. You cannot just maybe you work for 3-4 years and you'll finish, you'll reach your conclusion, but that's just not desirable. So for this, we devised a sequential approach in which we did screening of 5 ingredients from 11, and that we did based only on the main effects. Then from those 5, we screened a combination of 2 and 3 ingredients to find which of these combinations is performing the best. And then in step 3, once we have selected these 2 or 3 combinations together, we find out which of those combinations is performing best. And finally, we reached at the modeling part where we use predictions from the model to find the optimal level for those particular ingredients from that particular combination. And we will go in detail for each of these steps. So for factor screening, what we looked at now, we did 1 factor at a time, although like when you take a DOE class, this is something that you don't want to do. But in this particular case, we couldn't do screening design. And the reason was that there are inherent assumptions when one thinks of screening design. And that is that each factor can be changed independently of the other one. And then all factors are present at every run. And that is not true for our case. We cannot just put 4 or 5 ingredients together in this particular recipe. That means we could only focus on just 1 ingredient. And secondly, when we think about modeling of screening design, we build just 1 model and look at our parameter values. But in this particular case, that is not possible, because as soon as we start putting more ingredients in, we are moving away from our project objective. And finally, we didn't consider any interaction at this stage. First of all, it's just going to increase the number of runs drastically. And secondly, the way in food formulation and the way our mouth perceive interaction is quite different than usual process conditions. So there could be synergy, or they could be working against each other depending upon the dosage that we have put it in. So we already know there will be some kind of like a nonlinear effects over there, and including them at this stage just doesn't make sense. Now, if we consider then one factor at a time, we did that at three different levels in this case, 0.33, 0.67, and 1. And based on that, we did total 33 runs. And of course, we have our replicates. But throughout this presentation, when I'm going to focus on the treatments or runs, I'm not including replicates in there. So in this case, we have 33 individual unique runs. Once we performed those lab trials, we built a correlation matrix based on our desirability of each response. So on the right, what you are looking at is just to help you visualize. For 3 of the response we want to minimize, 2 of them we want to maximize, and rest of the 2 should remain unchanged. So this is the correlation heat map. On x-axis, we have our in all of the ingredients, and on y-axis, we have all of our responses. Now, just like written on the top right side, 3 of them we wanted to minimize, and we see like, okay, they are being minimized. Now we need to decide upon which one is the best. Then y4 and y5 we want to maximize, and y6 and y7 should remain unchanged. But correlation only tell half of the story, because you could still get a very good correlation even if response value from level 1 or level 3 doesn't change very much. So for this reason, we also looked at covariance heat map. Now, covariance actually tells us a relative change in response variable compared to unit change in your ingredient variable. So by combining both of these two informations together, we were able to eliminate 6 out of these 11 total ingredients. Now, if we just look at ingredients which are left, we see that our 3 variables, response variables, which we want to actually minimize, we have very good negative correlation with that. Then either we are not increasing our response variables which we want to maximize, or they are being maximized. And for rest, y6 and y7 in this particular case, we have a not very good correlation. That means they just remains unchanged. So this is what we desired. So in this first step, we have reduced from 11 to total 5 ingredients. And then if we go to the next step, I'm just going to call them now 1 to 5 just to make it easy. They are different than the original 1 to 5, but just for our next conversation, I'm just going to call them x1 to x5. And now we are actually interested in evaluating all the possible combinations and finding out which combination performs the best. So we have 2 ingredients. If we think about combinations, there are 10 for 3 ingredients, then we'll get 10 combinations. And in total, we have 20 combinations. And if we want to do now full factorial design for main quadratic and interaction effects, that will result in 330 different runs. And once again, that is already too much. And then we have our individual components, and it results in total 340 duplicates, which is, again, we don't want to do that many experiments. It's just going to take too much time and resources. So now, to overcome this problem, what we decided to do was that we are going to design 2-factor experiments where we have 2 ingredients, and we're going to combine all of that data to get design matrix for 3-factor combination. I will go in more detail on how it looks like. And for 2-factor experiment, we can use maximum level of 0.5. And for 3-factor, we're going to use maximum level of 0.3. So if we now consider just one particular combination, x1, x2, x3, then we can combine all of the data from x1, x2 two-factor combination x1, x3, and x2, x3. So that means we don't have to do all the experiments separately for three-factor combinations. And if we go in a little bit more detail for only one particular combination, so the approach looked as following. So first we design two-factor combinations using space-filling design, and we treated them as continuous matrix from 0 to 0.5. Then we did the same for three-factor design, but then we consider it to be ranging from 0 to 0.33. Then we combined all of these treatments in one table for all two factors and three-factor runs. And then we use a covariate factors function of custom design module in JMP to reach at our final design. And now let's go in detail of each of these different steps. So in the first step, like I said before, we created 30 different runs for two-factor combinations. And this is how our parameter space looks like. It's, of course, the same, only our x and y variables are changing for x1, x2, x1, x3, and x2, x3. So we are trying to explore all of the parameter space in this particular case. Then we did the same, but for three-factor combination, but our maximum limit is now 0.33, and we are again using a space-filling design for this. We can combine all of these runs now in one table, and if we visualize this, this is how overall all of these 120 runs look like. You can see on the walls, we have our two-factor design and runs, and in the middle, which is shown with the red dots over here, we have our three-factor runs. And when we are considering two-factor runs, that is 0 to 0.5. And when we are considering three-factor combination, that is 0 to 0.33. Then we can actually open up our JMP custom design module, and we can select this covariate factor button. And we can select all of these three columns in which we have all of these different values. And then the model that we selected over here for custom model include main effect, our quadratic effects, and all of our interaction effect. Then we tried different number of runs, 16, 19, 22, 2, and then compared them with each other and did the design evaluation to find out minimum number of runs required to get the best design possible from all of these possible 120 runs, to which results in this model. And what we found was that this kind of design actually gives us good optimality criteria, and the correlation between different terms in our model is quite small. Now, when we looked at this closely, it looks quite similar to full factorial designs, because what we have on our walls, in this case, two-factor combinations, we have points spread out in the corners, and then the design added 2 points for three-factor combinations. However, design also add central points in this case. So this was our first clue that we can actually go with the full factorial design in this case. Now, in hindsight, maybe we should have started there, but I'm just describing our workflow over here. So because it looked like full factorial design, so this is what we went back actually. So now for everyone knows, like if you have full factorial design, this is how the design matrix look like. And in this case, maximum is 0.5. And if you have full factorial design, for three combinations, this is how the design matrix looks like. However, now, as I discussed before, there is one extra point for full factorial design, which we have included ourselves, which is at the maximum limit for three-factor combinations. Now, in this particular case, these are the runs which are important for interaction and quadratic effects. And these are the runs where only one factor is being changed. But we have already performed these experiments where we looked at main effects in our first iteration, first step that we did. So instead of performing these runs again, we just augmented that data over here. That means in our step 2, we only need to perform the runs for these particular ingredients where either 2 or 3 ingredients are being changed. And this reduced our total number of runs quite drastically. From 340 runs, we could only do this now with 60 runs, and we could evaluate all of different 20 combinations together. Now, crucially, if full factorial design is actually orthogonal, in this particular case, we don't have orthogonality. So that means this is something when we are doing analysis, we need to keep in our mind. And total number of runs in step 2 then reduced to just 50. So once we have performed all of these runs for all of the possible combinations, what we did was we did a multi-objective evaluation, and that is we computed a distance metric compared to our target. So we have our target for y1, y2, y3, y4, y5. We want to minimize, maximize, and then we want to keep 2 of them constant. And then based on this distance metric, we found out which of the combinations are closest to our target and which of the combination results in not so close to the target. And the top 10 runs which are closest to our target, we found out which combinations are most prevalent in those top 10 runs. And those combinations look something like this. So we found two molecule combinations and three molecule combinations, which resulted in the best being closest to what our project objective was. Then just to, even though we know that our model is not going to work well over here, we still don't have sufficient data, and there is also non-orthogonality. We still wanted to see how the model is going to look like for each of these combinations. So for these 5 that I've just described, this is how R2 square look like for both 2-factor and 3-factor combinations. And in this particular model, we have our main effects, we have interaction effect, and we have our quadratic effects. Now, if only we focus on 2-factor combination for one particular of these combinations, this plot shows actual p-values. And what we noticed was for some of the response variables, p-values were, there was none of the parameter was significant. And for some of them, some of the parameters are significant, but they are not the same across different responses, even though we get good R2 score in this case. And that is to be expected because we have a limited number of data set and we are model may be overfitting in this case. And same was true for 3-factor combination. But what we realized for 3-factor combinations, at least 1 or 2 parameters are significant for all of the responses. But once again, not all parameters are the same, which are significant for all different responses. So that was the first clue for us, basically, that each parameter need to be modeled actually differently. And for each parameter, we need to find out which, each response parameter, we need to find out which of the factors are significant. So just to now illustrate this point more, for next, even using this limited data set, we removed quadratic effects. And then our R2 scores actually became really bad. So what this was actually a hint that quadratic effects are important for some of these parameters and we need to include them. So when we went to actually step 3, out of these 5 combinations that we looked at, now we only consider the combinations where 3 ingredients are present, because not only we could model them well, but our factors had an effect on these parameters. And now we need to find out which of these factors are affecting what response. Now, to augment data for these particular combinations, we added 5 additional runs using Augment Design module from JMP, and we use space filling design for this. So now, for each combination, we have at least 28 data points based on which we can evaluate a model. But as I highlighted before, for each of the response variables, model is going to look different. Now, we could go in and just try to, for each model, we can find a good model. But instead of that, we used a machine learning approach in which we evaluated different models for each response variables using ordinary least square approach, lasso and elastic net. But we also added support vector regression with only linear and polynomial kernel. And then we did a cross validation using leave one out method. In this particular leave one out, if you don't know, like what happens is that model is fitted on all of the data except one. And then that one data point is used to make the prediction, and then an error is computed. And this is repeated for all data points. And then you can compute your average root mean square error. And based on this error, then you can find out which of the model is best. What this allows you to do is it restricts overfitting, because you are always leaving one data points for prediction, but it still allows you enough data points from our limited data set to fit a good model. And once we applied this, what we get a good model for X2, X3, and X4 combinations, for which we get very low mean square error, and we get quite good R-square score. And because our capability to predict this particular combination is good, this tells us that unexplained error for this particular combination is less. So this is the particular combinations with which we move forward with. And this is how actually actual versus experimental and predicted values look like. And you can see models are not perfect, but still they are good enough to make prediction for this particular combination. So in next step, we use these models to actually run Monte Carlo simulations. Using those Monte Carlo simulations, we again computed based on response a distance metric, and based on the distance metric, we found out which are the simulated values are closest to our particular target. And then we performed clustering on all of those simulations which are closest to the target to find 3 different runs, which we can go back to the lab and do the experiment with. And out of those 3 runs, 1 run achieves our desired goal. We were able to minimize Y1, Y2, Y3, maximize Y4, Y5, and maintain Y7. At this particular step, we actually skipped Y6 because our ability to predict Y6 was greatly still not there even after all of these runs. And now going back to the again product workflow, this was just one step in all of this. Now we have reached at the lab scale, end of the lab scale. Now this is going to go to pilot plant. We're going to test scalability, then factory runs, and then rest of the things. And this brings me to my summary slide. So in this particular case, we used iterative DOE approach, stepwise, in which we were able to find out optimal combination using only 100 experiments instead of 500. And then space filling design was effectively used with machine learning to explore the experimental space. And finally, lastly, we found out that having this capability of machine learning combined with DOE data and this sequential approach, what this results in is allow you to find a better model, even if your hypothesis is wrong at the start. And yeah, with this, I'd like to say thank you.